In the previous video, we talked about the addition of protons to alkenes to form carbocations. How did that work? Well, the double bond came over, attacked the proton, and we got a carbocation. And the one we got was the one that was more stable, in this case, secondary. So we can draw the secondary carbocation in here. Now, what does this carbocation really do? Well, it all depends upon the counteranion of your acid. Let's say that we started off by using HCl. That means that for a second step, there would be some chloride sitting around from the HCl. So that chloride is actually going to serve as a base. Now, chloride is not a very good base, but it's a strong enough base to react with a carbocation because it is so incredibly acidic. So the chloride with its lone pair will simply come in, attack that positive center, and when we're done, we're going to get our chloride adding to that central carbon. So this net effect is we've added HCl in two steps, first H+, then chloride. The proton adds first to the N carbon to give us a secondary carbocation, and then the chloride attacks that secondary carbocation to give the chloride product. Now we're in the program OscarSyn, so we could have just asked the program to do this for us automatically. We could just draw an arrow down here and add an HCl molecule and press the magic button up here, and it would simply generate the chloride for us. Now, what about other acids? Well, other acids work just fine. We could add HBr. That's pretty straightforward. Here's, let's have an HBr. HBr, when added, gives the bromide. Not surprisingly, HI. Okay, here's HI, giving us the iodide. Now, so those halo acids all work the same way. Let's do something a little bit more complicated. Let's go back and form a carbocation and say, well, what happens if we use sulfuric acid? The reason I say sulfuric acid is a little more complicated is that sulfate is a really horrible base. Sulfuric acid doesn't really want to add very well, but it will. If you take sulfuric acid, it takes a little trouble to draw it out here, but draw out sulfuric acid, 4 oxygens, 2 double bonds, 2 OH groups. So here's sulfuric acid. Treat sulfuric acid on an alkene. Now, this is 100% sulfuric acid. What are you going to get? Well, you get a sulfate. And it turns out to be a very reactive compound. Its sulfates are not very stable at all. And the way you can see this is if you do sulfuric acid with some water around, okay, you don't form a sulfate. What are you going to do? You're going to form an alcohol. Why is that? It's because the sulfuric acid will add to the alkene in its first step, and that carbocation then won't react with a sulfate, a bisulfate. It'll react with water because the water is a much better base than the sulfuric acid. So sulfuric acid in the presence of water gives you alcohols. Going directly to the sulfate is not a reaction that people like to do, but this one works quite well. Now, what if we don't have water? What if instead of a water, we have an alcohol down here? What if you take methanol with some sulfuric acid? What are we going to get? We're going to get an ether, in this case, T-butyl methyl ether. Very, very nice way of making ethers. You can do a lot of these things. You can take, take a carboxylic acid, take acetic acid. Take acetic acid, and I say acetic acid as a base, that's got to be terrible. But it turns out that acetic acid as a base is better than bisulfate. So do the reaction, what do we get? We get a ester. So these are all acid catalyzed reactions where sulfuric acid is furnishing the protons, but the base is the solvent. And we need water, alcohol, and carboxylic acids. So you can do a lot with this reaction.